For the next set of problems, we are going to simply find the degree, the lead term, and the leading coefficient for each given polynomial. So as I look at this one, this is function notation, and it says it equals a negative 9x. So I know that my lead term is a negative 9x, okay? The degree is going to be a degree of 1. So this is the lead term, okay? The lead coefficient is going to be a negative 9 because that's the big number in front, and the degree is a 1. Degree is 1. So let's try it again, since that was just an absolute mess. We have 2 plus 3x squared. And the first thing that I notice is that this is not in descending order. So I'm going to go ahead and organize a little bit and rewrite that as a positive 3x squared and a positive 2. So now that it's in descending order, it is much easier to identify my lead term. So my lead term is going to be a 3x squared. My lead coefficient is the constant in front, which is a 3. And then my degree is going to be a 2 because that's the exponent that's attached. Let's do it again. All right, so I have f of x is negative 6x minus 5x to the 5th minus 8x to the 4th plus 3. And again, the first thing I notice, this is not in descending order. So I need to put this in descending order, which means this term is going to go first. So I have a negative 5x to the 5th. Here's an x to the 4th. So he's an 8x to the 4th. I don't have an x to the 3rd or an x squared. So negative 6x and positive 3. So my lead term, once it's organized, is going to be a negative 5x to the 5th. My lead coefficient is going to be a negative 5. That's the constant that's being used as a multiple. And then my degree is going to be 5. Looking at D, f of x is, now these ones are a little bit different. D and E are set up slightly different. So I've got an x to the 5th times a 2x minus 7 squared. So in our previous examples, all of these were joined together with addition subtraction. This was joined together with addition subtraction. This is joined together with multiplication. So I'm going to do a little bit of work in my head, and what I'm going to notice is that I already have an x to the 5th, and I'm going to be multiplying that times a 2x squared. Okay? So as I work this one, I really don't care for the purposes of this video. I don't care about the negative 7. What I should do if I wanted to expand this into polynomial form is I would do 2x minus 7 times 2x minus 7, and then I would distribute that x to the 5th through. But since all I'm worried about is my lead term, I can go ahead and get that done by multiplying what I have. So I've got an x to the 5th times a 2x squared, which gives me an x to the 5th times a 4x squared, because you have to multiply 2x times 2x, which gives me a 4x to the 7th. So if I were to multiply this whole thing out, combine like terms, put it in descending order, I would find out that my lead term is a 4x to the 7th. I've got a 2x times a 2x, because it's 2x squared, times that x to the 5th. So my lead term would be a 4x to the 7th, which means my lead coefficient would be a 4, and the degree of the whole thing would be 7, because you have 5x's being multiplied here and 2x's being multiplied here, which gives you a total of 7x's being multiplied together. So the last one is much the same, yet different. So we have f of x equals an x squared times 1 minus x squared times 4x minus 2. So I'm noticing that there's no exponents on the outside of these parentheses like there was here. So really, for me to know what my lead term is, I just have to multiply together everything that has x's in it. So this is set up as a multiplication problem. So I can take this x term times this x term times this x term, and that will tell me what my lead coefficient is and my lead term. So my lead term would be an x squared times a negative x squared times a 4x, which would be a negative x to the 4th times a 4x, which would be a negative 4x to the 5th. Okay, so watch your signs here. This negative up here is attached to that x squared. So what's my lead coefficient? My lead coefficient is a negative 4, and then what's the degree? Ooh, I can't spell. What's the degree of that term? It's a 5. So another way of looking at that, I'm multiplying 2 x's here, and then look in this clump. I'm multiplying 2 more x's. Look in this clump, I'm multiplying another x, so I'm going to be multiplying 5 x's together. I'd accidentally paused the recording, and I thought I forgot to press record, and I was hyperventilating, thinking that I just recorded a whole bunch of stuff, or didn't record a whole bunch of stuff. But it's okay. Nobody panic. I recorded it all. Okay, so one of the things that we need to know is we need to talk about turning points. So turning points, which we'll find out how to figure them out first, is going to be your degree minus 1. And that will give you the maximum number of turning points. So listen to me carefully. That gives you the most. That doesn't mean it has to do that, but it's going to give you the maximum number of turning points. So looking at the graph that we are given, we're given 3 different graphs. Okay, so looking at this first one, a turning point is where it changes direction. So if I'm reading this, right now it's going up, and then it's going down. So this is a turning point. Okay, so if the maximum number of turning points is the degree minus 1, okay, that means that this must be a second degree, because 2 minus 1, let's look at it this way, 2 minus 1 would give me my 1 turning point that I have. Focus. Okay, so looking at this, you should recognize that that's a parabola anyway. So what we are going to do, I'm looking at the graph, I'm determining the number of turning points, I'm seeing that there is 1 turning point. The smallest possible degree that this polynomial can have as it's graphed is a second degree, because the degree minus 1 is the most number of turning points. So degree of 2 minus 1 is 1 turning point. How many intercepts do I have? I've got 1 here, and I've got 1 here. So my degree is a 2, and the number of intercepts I have is a 2. And then our end behavior, which we've done before, is as I move to the left, what does my tail do? So what I can say is if f of x, that's not what I wanted to say. Stop that. If x goes to the left, then f of x goes down. Okay, so as x goes left, the tail goes down into negative infinity. So do it again. If x goes to the right, so if x moves to the right, where does my tail go? My tail on the function goes down to negative infinity. Okay, and then is your range restricted? So I do know that these are going to be going down for all eternity, but it also tops out right here. So where does this top out at? It looks like about 1 1/3, and unless we actually know what the graph or what the polynomial is, we don't know. So if the range is restricted, yes, my range is restricted from negative infinity all the way until I get up to wherever this peak is, which it looks like it's at about 1 1/3. So we're going to say 4/3, okay? So my range would be, remember range references y values. So I would have all of these y values all the way up until I hit about 4/3, okay? So let's try it again. we have turning points. So here's a valley, here's a peak, here's a valley. So I've got 3 turning points. So 3 turning points. So add 1 to that, and that's the smallest degree polynomial that you can have. So my degree is a 4th degree polynomial. Okay? So 3 turning points, add 1 means it's a 4th degree. That's the smallest it can be. Okay? How many intercepts do I have? Well, looking at this, I've only got 2 x-intercepts. So let's think about that for just a second. If you'll notice, this little part right here looks a little bit like a parabola. Those 2 solutions would be imaginary. So you're only seeing 2 x-intercepts out of a 4th degree. Your other 2 solutions will be imaginary or complex. Okay? And then what's your end behavior? My end behavior is if x goes to the left, where does my function go? If I move left, my function's going up. So my function goes to positive infinity. What about if x goes to the right? So as I move to the right, where does my tail go? My tail goes up to positive infinity. And then is the range restricted? Yes, the range happens to be restricted this time because it's never going to be anywhere down here. So what's the very, very, very lowest that this can be? The lowest it can be is about -1.5. So we'll say -3/2, which is about right here. Okay? And then it's going to be up for all eternity. So I've got y values for the rest of its life. So let's look at this one. Okay? I would like to know, first of all, how many turning points do I have? So I've got 1, 2, 3, 4 turning points. So 4 turning points, add 1, and that's the least possible degree you can have. So this would be a 5th degree polynomial. Okay? And then how many x-intercepts do you see? I see 1. There is 1 x-intercept, which means where are your other 4 solutions? The other 4, because I'm looking for 5, that's what the degree says. If I've only can see 1 hitting the x-axis, then the other 4 must be imaginary. Okay? What about end behavior? If x goes to the left, so as x goes to the left, where does the tail go? The tail goes down to negative infinity. If x goes to the right, where does my tail go? My tail goes up for all eternity. Okay, which means if it's going down for all eternity, if it's going up for all eternity, my range is not restricted. So my range is all real numbers. Because it's always going to go forever down. It's got these little hiccups in here, and it's going to go forever up. All right, so looking, let's do these now. So I'm going to look at the equation. In the last example, we did the, what did we do? We did the graph. Now we're going to do the actual equation of our function. So for part A, we have f of x equals x to the 4th. So what am I supposed to find? Analyze the equation, determine the degree. So what's my degree? My degree is a 4. Degree is a 4. Okay, the maximum number of turning points. Well, your maximum number of turning points is your degree minus 1. So turning points is going to be 3 or less. So the maximum number of turning points is 3. Okay, how many intercepts could we have? So look at your degree. My degree is 4. So my x-intercepts, I could have a max of 4 x-intercepts. Okay, and that reflects straight off the degree. What is your end behavior? So on this one, I know that it's even. And if it's even, my arms are going to go up in the same direction or go down in the same direction. So if it leads off positive, my arms are both going to go up. If it leads off negative, my arms are both going to go down. And since this one leads off positive, my arms will both go up. So for end behavior, what I am looking for that is as I move to the left, what will this tail do? So it's not this one because it did not get flipped. I'm leading off positive, so it's not this one. So as I move to the left, what is this arm going to do? He's going to go up. So my function will go up to positive infinity. As x moves to the right, what will my tail do? My tail will go up to positive infinity. Okay? And then is your range restricted? Yes, it is, because it's going to bottom out at some point because it's got to turn around to go back up. So in this case, my range is restricted. Okay? So let's look at B. For part B, we have f of x is x cubed. So this is n behavior for even degrees. Well, now we've got an odd degree. So what is my degree? My degree is 3. So what's the maximum number of turning points? The most that this can change, the most of this can change direction is going to be my degree minus 1. So 3 minus 1 is 2. So it might have 2 turning points. Okay, how many x-intercepts could I have? What is the maximum number of x-intercepts I could have? The maximum number of x-intercepts I can have is 3. Okay? So when I'm looking at that, if we wanted to find the x-intercepts, you would say it's equal to 0 and you would solve. You would say it's equal to 0 and you would solve. All we're doing is I'm trying to put all of this together in one package and we can do detail stuff later. Okay? So what is the end behavior? So for an odd end behavior, it's either going to look like this or this. If it gets flipped, it'll look like this or this. Okay? So this leads off positive, which means it's going to have this end behavior. So as x moves to the left, where does my tail go? It goes down. So for end behavior, as x moves to the left, my tail will go down. Okay? As x moves to the right, so remember this is if it's negative. I didn't lead off negative. So as I move to the right, where does my tail go? My tail will go up. So my tail will go up. And then since some stuff can happen in there, is your range restricted? No, it's not. Because it's going to go forever down and it's going to go forever up. Okay, so an odd degree will not have a restricted range. Not restricted range. So let's look at C and D, and then we'll look at the last one. This is going to be like an ultra long video. All right, so for part C, we have f of x is negative x squared times 2x to the third minus 3x squared plus 2. So I want to know the degree first. Well, in the first two, it was just set up as a single term. On this one, this is set up as a multiplication problem. Your bigger picture is this chunk times this chunk. So I need to know what my degree is. So the degree of this would be, take this chunk right here times the biggest degree in here, which is an x to the third. So my lead term here, so we're kind of putting stuff together, my lead term would be a negative 2 x to the fifth. So my degree on this is a 5. So what about turning points? Turning points is 1 less than your degree. So the most turning points I'm going to have is 4. Okay? How many x-intercepts can we have on a 5th degree polynomial? So we're being general in this question. I'm not asking you to solve this one. I'm just saying how many could you have? I could have 5. It's the same as your degree. Okay? And then we have end behavior. So this is a 5th degree, and it got flipped. So I'm leading off negative. So that means that to the left, he'll be going up, and to the right, he'll be going down. So for my end behavior, as x moves to the left, the tail will go up. As x moves to the right, the tail will go down. And then, is your range restricted? No, it is not restricted because it's going to go forever up and forever down. All right, last one that we have is f of x is 2 minus x to the 7th. So this is set up as a multiplication problem. So I need to actually figure out how many x's I'm multiplying together. So my degree, the way I'm going to look at this is I'm going to take my lead term and count how many times I'm going to be multiplying it times itself. Okay? So I have a negative, I said lead term, remember this is not in descending order. In descending order this would say negative x plus 2. So that's why I said lead term. So negative x, but I'm raising it to the 7th power. So I'm going to have to take 2 minus x times 2 minus x times 2 minus x times 2 minus x, blah, 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 until I finally figure out that I've got a negative x to the 7th power as my lead term. So negative x to the 7th. So how many turning points could you have? Take your degree minus 1. So I could have 6 turning points. How many x-intercepts could you have? I could have up to 7 x-intercepts. Up to 7 x-intercepts. And I get that from looking at my degree. What about your end behavior? This is an odd exponent. So for an odd exponent, he will either be going in, all right, here's how you can remember this. An odd exponent will go off in opposite directions. Okay, an even one will go in the same direction, either both up or both down. An odd degree will be in opposite directions. So this is leading off negative, which means it's going to have this same format. To the left, he'll go up, and to the right, he'll go down. So as x moves to the left, my function is going to go up. That's supposed to be an arrow. Good heavens. As x moves to the right, my function will go down. Okay? Is your range restricted? No, because it's going to go forever up and forever down. So it is not a restricted range. And now we can move on to the final problem of this section. So it says an oil slick is expanding as a circle. The radius of the circle is increasing at the rate of 20 meters per day. Express the area of the circle as a function of d, which is the number of days elapsed. Okay, so what do we know? So there's a little bit of weird things going on here. I need to know what I am doing. So hang on, I have the area of a circle is pi r squared. You can, the area of a circle is pi r squared. Okay. So the radius of the circle is increasing at the rate of 20 meters per day. So I need to know what the radius is. So if I have day 1, it would be 20, right? If I have day 2, it would be 40. If I have day 3, it would be 60. So what I'm going to do is take my radius and multiply it times 20. Okay, so here is my radius, and I need to multiply that radius by 20. And I'm going to put it in terms of d, because it's going to be 20 times the number of days. Okay, so if it's 16 days, it's going to be 320. Okay, so I need to square that part. So my radius equals 20 times the number of days. So I just swap that out. Well, now what can I do? I can square both of these. So this becomes 20 times 20 is 400 pi times d squared, where d is part of your radius, is the number of days, and it'll multiply times that. That was a really messed up explanation. All right, so I will see you for the last video.